Okay, welcome to Lecture 6. Over halfway home, and the fun part I think is even ahead of us, and things I think are going well. I'm appreciating all the good discussion on the board and all of that. So today what we're going to talk about is really solidification processing, and two parts of that. One is casting to make shapes. We'll get to that later. First, I want to talk about what happens during castings, and before we even get to that, I want to go through a few things that are related to things that have come earlier within the course. So let's do that first. So first updates. Number one, some of you have noticed I have not put grades for comments up yet. They will. Discussion grades will go up soon. Just forgive me that everything. I'm pleased with what's going on, and points will accompany that. The projects also we'll talk about. I really, again, as I've mentioned before, don't want to duplicate work for what we're doing at COSI. That will be a topic of discussion when we all are together at COSI on the 21st, and you'll hear a little bit more from me possibly ahead of that. I want to do things that are meaningful and are along the lines of what you're doing. As I've said from the beginning, I have no intent of giving you busy work that doesn't impact your knowledge or your relevant knowledge or your students' outcomes. That's what we really want to do. And then last time I gave some answers, asked some questions about some calculations about how many atoms across a grain and so forth. And so far, not a whole lot of people, under half the class has responded to that quiz. So I'm going to also wait on the answers until a few more people have responded, but those will come as well. So here's really what I want to make one of the central themes of this course is the reason students should care about this is we are providing science for making useful stuff. And if you know the science, you can make cooler stuff in your career, whatever that career might be. And really, material science, there's two parts of it. Most material scientists really concern themselves with properties of materials and tailoring the structure to make properties, and those properties include strength of the material, appearance, its luster, the surface finish it might have, so forth, durability, be it against corrosion or fatigue, thermal conductivity and the like, melting temperature and the like, electrical conductivity. These are all examples of properties, and we can put units often with funky dimensions on them. MPa, force per area, and so forth. Corrosion rates, we get funky units, all of that. And properties are important, but properties don't buy us too much when we're actually making stuff. What we really need is its properties plus shape often that makes what we have. Even if you look at an integrated circuit, it's where you shape, where you put the conductive bits and the various dopants that makes it happen. Shape, and I'm talking mostly about mechanical stuff here, is something that we're very interested in. So we've already seen springs have very different response than basic wires because of their shape. Automobile components have a certain shape to optimize strength and minimize weight. Your cell phone has a certain shape. Structures, we like I-beams because if you take an I-beam shape, make it long this way, you actually at fairly low weight, you end up with very stiff moments this way with modest weight on the beam, much more efficient than if you were to have just a plain old block. That's why we use I-beams. Lots and lots of examples of that. And properties plus shape really gives you manufacturing. And that's one of the things I'm very interested in, is how do you run a process that gives you good properties in the material, useful shape, all does that cheaply, and there's a huge amount of room for creativity and careers in that basic space, and that's really where we're going, and the federal government's actually paying a lot of attention to manufacturing these days. It's one of these things that we need for a robust economy, and skill levels all over the place, from PhDs to people who are really proficient with their hands are needed, and you guys as teaching the next generation are in a great place to do that. So we're going to get back to that, and let's talk first again about maybe the properties. And mechanical properties are something we've talked a fair bit about. And here's an example of several aluminum alloys. And the alloy that we tested first was pure aluminum, and pure aluminum, we have these funny numbers that mean they have standards that have to do with the composition and structure of these materials. This is pure aluminum. This is what we tested before when we made those wires out of pure aluminum back in lecture number 2 or so. What we can do is we can modify the chemistry and the microstructure to actually get much higher strength of these things. So you see this represents the strength. This is about the yield. This is about the yield strength for pure aluminum. And you can see I can take 5083, which is an aluminum magnesium alloy, get much stronger. We can take age-hardening alloys, 6082 and 7000 series. These are more like aircraft alloys, much stronger than pure aluminum, still have good ductility. But the important part is the way we measure that is with something that we call a universal mechanical tester, and these things are usually on the order of, say, about a good one might cost you $100,000. Not something you're going to get in your high school, but that allows you to make measurements like that. Point I'm going to make to you, you don't need this thing. The other point I'm going to make is the things you can measure in the high school. We can measure modulus, we can measure strength, and then you can compare things. For example, this is this aluminum alloy over here, very similar 15083 that you had here. This compares it to mild steel. You see that they have about the same strengths, little different characteristics, but one thing you see is very different, and that's the elastic modulus of aluminum is about a third of that of steel. And again, this is something you can measure, and you can see that plastics actually have much lower modulus. And you're not going to do it really accurately in a high school classroom, but you can do a pretty good job. And that's shown here. This is basically the test that I went through. I think it was in lecture 2 when we talked about testing of wires. I had my very good undergraduates, Connor Sloan and Katrina Booz, test pure aluminum wires that we bought at McMaster Carr. First thing they did is took these 25 thousandths diameter wires and hung weights from them, measured the length, and as a function of the weight that's put on. So they kept increasing the stress, measured the strain, did this with 3 different replicates, found it to be very reproducible, and we could put this into stress. And again, this is megapascals, is millions of newtons per square meter is what that unit is. And then they could also take this and look at different wire diameters. These are the 3 tests that you see over here. And then here's a smaller diameter wire. Here's a smaller diameter wire yet. And what's really interesting is these take a much smaller force because the diameter is not quite half, but the cross-sectional area is probably about half. But if you plot this the right way in terms of stress strain, you get the same plot out of all of these. So again, you sort of get a master behavior for the material that can be very useful in predictions. And so if you were to do a thing in your class where you said, okay, let's predict how wire force to failure scales with cross-sectional area, you could do some nice things with this and engage math. So one of the things that's really fascinating to me that is coming out of the discussion boards is, a lot of comments like, gee, my kids don't really want to do math and science, and that's a different thing. And I think I've ranted a little bit about this on the discussion board already in a form of a question. But to me, engineering, science, technology has to have math in it. It's a predictive thing. This is why people can make a living with it, because they can predict what's going to happen when you change conditions. It's not qualitative. We do science with adjectives. We do science with numbers, not adjectives. Political scientists, politicians, other forms of BSers just use adjectives. We have to make real predictions in science and math, and so I think, going back to this, there's some really nice, meaningful math opportunities that we're going to try to tease out of this, and hopefully talk about this when we see you in COSI next, and maybe develop a little further. But we can do graphing with this. We can do experiments plus analysis that lead to predictions. So if you have a really big wire, how much load can it take? What would it take to haul? If you had a wire that was going to be used to connect a car and a trailer, can you tell how big a wire you might need? One of the math standards that's big in high school is numbers and quantity. Basically, dimensional analysis, pounds per square inch, miles per hour, furlongs per fortnight, all kinds of those things. And I think examples like this can really break down the silos between science, technology, engineering, and math. It's an amalgam of all these things. The science is really the fundamental understanding. Engineering is putting numbers to it. Making predictions to make things is technology. And again, math is kind of the big integrator. And I really think, and this is the way the later science standards go, is trying to break down these things and break down these silos. And so if you are working with the math department, I think there's some great opportunities in this, and we'll talk about more later. So that's properties. The other thing we talk about is shape. Shape is another really important attribute if you're going to make anything useful. And we've already talked about making a spring, and we can make a spring by plastic deformation. And there's really two ways of doing this, at least. There's way more than two ways. But one way, we mentioned the drill, where you can take a drill, put a rod on the end of that, and basically use the drill to spin it, and then hang your wire here and make a spring. And this would be the chucked end here, and you'd chuck one end into that, and you can make a really nice spring that way. And if you can kind of keep the force consistent, you can make some very consistent winds with it. Also, you can do this if you just have a mandrel. You can also wrap these by hand and do pretty well, but it's a little trickier. You don't do quite as well with the drill, but you can still make the shapes basically by plastic shaping of this. And as you just try to do this with strong and weak metals, make strong and weak springs, you'll see there's very big differences in how well they set. There are a number of teachers that say, boy, I could be some danger in bringing power drills into my classroom. But I know when I was that age, I was fortunate in that we had tools in the house, and I was, regularly messing around with things like drills back in that day. So plastic deformation, the point is, this is one way to make a shape. The other way you can make a shape that's very common, and these aren't the only two, is by casting. And we're going to show that we can use these silicone molds that can be used to make shapes. And what's cool about these is there's all kinds of things that are available. You can make rings, you can make shot glasses, ice shot glasses. I think that's the same thing. Hearts, robots. And we'll show that if you have good low melting alloys, these make a nice way of making some pretty cool things. You probably don't want to make guns in your classroom, but those things are all available. Pac-Man, kitties, all that. So that could be a nice demonstration, and there is a lot of science in there that we'll show. So today what we're going to talk about is really we're going to focus on primarily solidification. I can't really talk and write at the same time. Phase diagrams and casting are things, and we're going to talk really about what is a phase diagram. And in material science, and all of you people who have a chemistry background know about phase diagrams, we're going to use a particular form called a temperature composition phase diagram to show, number one, how many phases exist at a given temperature and composition point. Secondly, we can talk about what the composition of each phase is. Third, we can talk about the volume fraction of each phase. And lastly, and we're going to go fairly quickly over this just because of time, the phase diagram, and if you know how fast things solidify and a few other things, you can really predict what the structure is going to look like. And that does get into pretty deep material science in a hurry. So here's the phase diagram we're going to deal with. Another really nice one to deal with is the lead tin system, and both of these are used as the basis of solder alloys. Lead tin has been the favorite over the years. It has some very nice characteristics. Lead is a material we don't like to use so much. Bismuth we can do some great things with, and I think a lot of you have probably also seen as part of the ASM series just bismuth hopper dendrites. Just if you solidify bismuth on its own, it makes these really cool crystal structures. Also, when bismuth solidifies, it has a density that's less than that of the liquid, which is unusual. Ice does the same things. Most things, when you form a solid, it's denser. But you can solidify bismuth on its own, or in this phase diagram, you can do some nice things with it as well, as we'll see. So phase diagram, what we're going to deal with is this axis is temperature. In this case, it's in degrees Kelvin. This is percent. You usually go from A to B. In this case, you're going from bismuth to tin, and this is usually in weight percent. In this case, it says mole percent. You can do it either way. But what you see here, just off the bat, just to give a little preview, this is the melting temperature of bismuth. It's about 550 degrees K, so subtract 273 from that, so you're 250 degrees C-ish. This is a eutectic point. We'll get to it in a little bit. This is pure tin. This is the melting point, quite a bit higher than eutectic. And you've got different phase regions here, where this is liquid. This would be pure bismuth phase. This would be pure tin phase. And this would be solid bismuth plus tin, and it's a mixture basically of two solid solutions. So this is maybe a level of complexity you don't want to get to, but this is the way the real world is it's not kind of element, mixture, compound, solution. This is a mixture of two solutions, and this is very, 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 very common in materials science. It's something that I think is teachable as well. But this is mostly in the spirit of making you smarter than your kids. So here's what real aluminum alloys actually look like if you have a powerful enough and clear enough to understand microscope. They're very powerful, but often it's a little difficult to understand the images. This is what we call phase A. Phase A is a solid solution of aluminum plus copper, and you can see this is aluminum, and there's a few coppers around. That's what we call a phase. That's an area that's chemically distinct and understandable. This is another phase, B, and you can see this is ordered. This is a compound, and that's a second phase, meaning that it has, again, sort of a very particular compound organization. You can analyze that. It has its own properties associated with it. And what we're going to do with phase diagrams is you've got those two phases, and we're going to ask the questions at any given composition and temperature, so long as things are in equilibrium. And that's kind of an if that I'm going to gloss over. Ask me questions if you like. We're going to answer one, how many phases do you get? Second, what's the composition of each phase? And then thirdly, how much of each phase do we get? And we're going to kind of gloss over this one a little bit, but it is well-posed algebra if you understand the rest of it. But again, this gets a little too much for 9th grade probably. However, if you'd like to do a grade 11, 12 intensive material science course after physical science, I think all of this could go into that very, very nicely, and I'd love to help make that happen. So here's what we have. So let's consider components and phases and bring this into what real material structure looks like. And we introduced that last lecture. So our components in this case, let's imagine we've got bismuth and tin. Those are our two primary components. It's a two-component system. Those things can either form compounds or solutions or stick as pure elements. Just by thermodynamics, things almost never stay as pure elements. But phases we just define as regions that are physically and chemically distinct regions. And each of these phases has a given composition associated with it, which is the amount of each component that goes into those phases. So bismuth and tin, or this is an aluminum copper alloy. Actually, it's been solidified. And you see, in this case, two regions that are interconnected. We call one phase alpha. We typically put Greek letters on these, which is probably mostly just confusing to people in high school, but that's what we tend to do. And then we name the other phases beta, the lighter stuff. And you can see this is kind of what a solidification structure tends to look like. You get these fantastic structures just by the way nature happens, and you get these things. And this really is a mixture of two solid solutions, meaning that this would have alpha would be primarily aluminum plus minor amounts of copper, and this beta is actually an aluminum copper compound. And with undergraduate labs, I've worked a lot with this aluminum copper system. It's too difficult to work with in a high school environment, but you get remarkably beautiful microstructures very easily, and there's also a lot of commercial and technical interest in exactly that system. So it's a good one. So this is a phase diagram you may have seen before. This is again in the form of temperature composition, and this is one that you'd probably see in chemistry, is an ice-salt phase diagram. And the two components here would be water and salt, NaCl and H2O. And you can see different phases here. Brine is, by definition, a solution of salt and water. When you add salt to water, it depresses the melting temperature. That's why we often do it. If you get down to about minus 20 degrees C, you'll even freeze the brine. And that's why if you get far enough north, they don't even bother with ice anymore. They'll just put sand down to try to make the ice a little less slippery. But you see this is broken up into these regions. This is all ice along here. This is ice plus brine, brine plus a compound. And these are our regions. And you can see there's solubility limits on this. If you imagine you're in this region here, we've got ice and brine. Let's imagine a composition point here where I've got, say, 5% sodium chloride in water, and I'm sitting here at minus 10 degrees C. I sit like that. If I blow that up, what do you imagine that looks like? I've got this thing, I've got brine, and then I've got ice that's in there. Well, you probably know if you put ice in salt water, does the ice get salty itself? Well, it really doesn't. The salt doesn't want to be part of the ice. That's why it segregates out. So you actually get something that's interesting. You get this composition of liquid, or this composition of solid ice, which is basically pure from salt, might have a little salt in it, and this composition of the brine. The brine is actually going to have more salt in it simply because about half the volume is taken up with ice. And the ice doesn't have any salt, so by conservation of volume, the salt has to be pushed out. So you get saltier brine, less salty ice, all sitting in that system. So again, what we've shown very quickly, and we'll go through this a little bit more systematically, is if I pick that composition point, number one, I know I've got two phases there, brine and ice. I also can tell you what the composition of each one is. You've got ice that has almost no salt in it, and brine that's quite salty. And then we could use a third thing called the lever rule that I'll introduce in a little while to say, it's going to be about half brine and half ice under those conditions. You can see if I move all the way over here, so I have very little salt in it, you can imagine it's going to be mostly ice in that situation and a little bit of brine. And that brine's actually going to have the same composition associated with it, but it'll be a lot less of it. So it's interesting, and there's a lot of predictive power in these phase diagrams. I think these are very rarely taught, if at all, at this level in high school, but this is absolutely a staple of being a professional material scientist / engineer, so you can put people way ahead of that. So again, we can take these, we can imagine changing temperature or composition. Imagine I'm sitting up here at brine, that's at 10 degrees plus. Go down, I get about 5% salt. Go down, I go into this two-phase region. It's going to be fairly pure, salt-free ice and salty brine associated with it. But I could also take that and add more salt to it to the point where it'll all dissolve to be a saltier brine with no ice whatsoever. So I can change temperature and composition on these diagrams. That's commonly done. So let's consider a real metallurgical system. This is copper nickel, cupro-nickel as it's sometimes called. And it turns out that nickel and copper are fairly similar with respect to their atomic structure. They're both metals. They both have the same crystal structure. They have similar electronegativity, very similar atomic radii. And there's this guy, Hume Rothery, years ago, and he said, yeah, if they got the same crystal structure, the same electronegativity, about the same radius, it's likely that they'll just mix and make a solid solution. And indeed they do, but it's not quite that simple. And so this is what the phase diagram looks like for the copper-nickel system. And again, this is composition on this axis. This is weight percent nickel in that case, and this is temperature going this way. And again, I can pick any point on this, pick 3 random points on there. At this point, everything is all liquid, and this is again very high temperature, and this is be about 65% or so nickel in copper. That's that one. This point here, similar composition, lower temperature. What you expect to have are 2 phases here. You expect to have a liquid of this composition, and the idea is this line I'm drawing should be parallel to this this x-axis. So you should have liquid of that composition in equilibrium with a solid of that composition would be what you would expect. You're going to expect that the solid is going to be more nickel rich because the nickel has a higher melting temperature than the copper is what happens, and then you're going to segregate more of the copper out into the solution. And then down here, this would be all solid, and you'd expect in equilibrium it would just be this particular composition, that temperature, and it's all going to be solid. So what you've got here is you've got 2 phases, liquid and solid, and 3 phase fields, this being 1 phase field, this being the other, that being the third. So the 3 phase fields you have is all liquid, the solid, and the liquid plus solid. I should give them the same numbers, are the 3 phase fields that you end up seeing. Okay, hopefully you're with me on that. So so the first rule of phase diagrams, if we know temperature and composition, we know the number and types of phases present. So for example, I think this is one that, no. So for example, if I'm at 35 weight percent and 1250 degrees C, 1250, 35, it's going to put me right about there. I'm going to say that's going to be single phase liquid just above that. And if I do A is 60% and 1100 degrees C, this would be all solid down here. And if I picked another spot in there, that would be 2 phases. Okay. So if you do that a little bit more carefully, I think this is the second rule of phase diagrams. If we know what the temperature and composition is, we know the composition of each phase, and C sub O is the overall composition here. So the examples here are let's imagine it's 35%, and you're sitting here at T sub B, and at that point your composition of your liquid is going to be about 30%. Composition of the alpha is going to be out here at about 42%. And at this composition of liquid is the composition of the liquidus, and the composition of alpha is the composition of the solidus. So the third thing we can get is you can get the weight fraction of each phase, and I'm not going to do too much with this, but basically if this point gets really close to the solidus, then you expect that it's going to be mostly solid. If this point of the actual composition point gets really close to the liquidus, if it gets really close to the liquidus over here, it's mostly liquid. If it gets really close to the solidus over here, it's mostly solid. So what we can say is we call this total length T from here to here. For example, the fraction of the solid would be equal to this distance R over basically that total length, and that's basically what these guys say. And I'm not going to waste time on that because I think this gets beyond where you want, and I'm going to skip that. But if you want to do that, there's nice mathematical proofs for that. I doubt you're going to do this in the ninth grade. The thing that I do want to get through, though, is that there is this interesting microstructural development that's very similar to the kind of microstructural development that you end up seeing if you just have just look at your on a cold winter day when you put a little of the wiper fluid on your windshield wiper. You see these dendrites form. You see a kind of a first bit form, and then it pushes solute off to the side. That's a mixture of water and some alcohol or something like that. The water tends to solidify first, pushing the stuff that doesn't want to freeze out, and you get very similar things with copper-nickel alloy. If you cool down, you end up first solidifying something that is going to be nickel-rich, and you're going to have, this is your solid, this is your liquid, and you're going to end up rejecting the copper out. And the microstructure you end up getting, even with this very simple system, it's all liquid at high temperature. You start to solidify the nickel out, nickel-rich material first. Here you're getting it where you're getting more and more enrichment of copper in the liquid, and the solid is becoming less enriched in nickel. You're able to, as you cool down, to incorporate more and more copper in the solid, and then you get to this point here where you've kind of locked in these nickel-rich regions, and then you've got these copper-rich regions there. So what you really have is an area it's all solid solutions, but it's a mixture of solid solutions of different compositions, and this is what the microstructure ends up looking like. And then if you anneal it at high temperature long enough, it'll diffuse away and become uniform. But this is what, let me pass by it. This is what the real microstructure ends up looking like. And the first bit to solidify are these nickel-rich dendrites along the middle. Okay, so these are the nickel-rich dendrites, and then these are the last regions to solidify, which are the copper, which are swept to the side. And that's what you end up seeing. So you get this segregation. Again, it's a mixture of regions of different solid solutions is what you end up getting. So here's your chord and equilibrium microstructures. Your phase diagram says if things cool very slowly, what you should end up getting is something that's really uniform. It looks like that. But that is if diffusion happens relatively rapidly. But normally what happens is you get this chord structure where you've got a nickel-rich region in the middle, and you've got a copper-rich region on the outside, and that gives you that structure that we end up seeing here. So it's all really very understandable, very manipulatable, and we can actually measure that nicely as well by using metallography. So the system that we will consider binary eutectic, and a good example of a binary eutectic is a bismuth tin system that we'll deal with. And got a eutectic composition here, and this is actually the copper-silver system. Copper-silver system actually sterling silver is silver with about 7 or 8% copper in it. And you can see that each of these regions, this is a region that's face center cubic copper. This is a region that's face center cubic silver. Has a different lattice parameter, a little different structure. They're closer together in one case than the other, the atoms are. But you can see that in the case of alpha, you can dissolve up to about 8% copper, or 8% silver and copper. And in the beta phase over here, you can dissolve up to about 9% silver, rather copper and silver. And these things have fairly high melting temperatures together, each of them. The copper melts at about 1100 degrees C, silver melts at about 900 degrees C. I should say ag there. But you get this region in the middle where it's actually melt at a much lower temperature. That can be actually very useful if you're making solders or brazing alloys or the like. And this is what we call a eutectic composition. And you end up getting a very fine solidification structure usually that ends up happening there. And this eutectic temperature is the lowest temperature at which there's a liquid. And this is your eutectic composition. So this is a lead tin eutectic, and I actually thought I had set PowerPoint to skip these slides. I was going to leave these, I guess, leave some of these slides out, and leave them in there if you like. But I guess this one I'll go through. This is a point here on this. What you expect to see here is a mixture of two solid solutions. This solid solution would be this would be lead tin over here. This alpha is going to have about 8% tin and lead, and the other phase here is going to have about 1% or so in tin. Then if you look at this thing will also be, it's closer to this side, so this is going to be by eye, about 66% alpha and about 33% beta, and those are the compositions. So again, point is, and this may not really work at the 9th grade level, but it's going to be a mixture of two solid solutions, and that's very, very common for most materials, and we can understand that. So some more detailed slides follow on the PowerPoint that I'm not planning to go through here. Hopefully it skips over these. Yeah, this is where I wanted to end up. If you want to go through that, please do. There's some great resources. I'll point you towards some of those that you can also use. But this is what you end up seeing in the end. This is the diversity you get out of a simple eutectic system, and lead tin is one, bismuth tin is another. Turns out this is an area we call hypoeutectic. This has less solute than you get for eutectic. If you go through this, the first thing to solidify is this alpha, and you see these big alpha blocks, and then on eutectic solidification you see this mixture again of two solid solutions, but they come together in a very mixed way. If you solidify right at the eutectic, you get these mixtures of two solid solutions. And then if you're here hypereutectic, this is the lead, the tin that solidifies first. And again, you get this eutectic structure in between, which is this very fine mixture of two solid solutions. So again, hopefully maybe these micrographs can give some meaning to your students between mixtures, solutions, and so forth. This is the phase diagram that's probably the commercially most important in the world, the iron carbon system. We make many, many, many tons of steel products based on this iron carbon system all the time. There's two systems in here. This point A is a eutectic, and the definition of eutectic is you've got liquid going to solid 1 plus solid 2. In this case, it's liquid, goes to this phase called austenite, which goes gamma plus carbide. And then we have the other thing that's really important. This is called a eutectoid, and here you've got this austenite goes to alpha plus cementite as well, or carbide. And if we quench quickly through this, we can make a very hard phase called martensite, and it turns out there's all kinds of things you can do with the microstructure here, including the slow cool. You got perlite, which is that structure there. And so we can get an amazing set of different microstructures, properties, hardnesses, and so forth, and that's why we like steel so much. So I have skimmed the surface of this, not even that, but what I do want to say is there's a really, really good site. There's a few really good ones. I think one of my favorite, and let me know if you think this is way too complicated or not. There's one out of University of Cambridge. This is, I forgot what exactly this means, but it's propagation material science with IT, technology, so forth. But I want to show you a couple of things on this with YouTube. Actually, just not YouTube yet, but just to show you the site. And we're going to keep our annotations here, and everything should keep working. Phone. Oh, come on. Oh, Debbie's crashed. Let's see if this works again. Okay, it actually surprisingly works. So this is this is the lead tin system, and what this shows is the phase diagram going across this, and then the micrographs are shown beneath this, and this shows what you end up getting. So back here, this is if it's predominantly tin, and you can see that there might be little pockets of bismuth that are in there, and if you zoom in enough, you see you're getting a little bit of bismuth decoration on the grain boundaries here, and this is 600 microns across, so a millimeter will go from here to about there. It's 200 microns across, that's 20 microns across. Let's skip to eutectic solidification, that's right here, and you can see this is this mixture where you have two solutions, one with about that composition, one with that composition, that are mixed together mechanically in a very fine way, and in a 600 micron resolution you can hardly see anything. You really zoom in to see much at all. You look somewhere in the middle of a hyper-eutectic. These are regions where you have first primary solidification of tin, then bismuth solidification in a eutectic manner near the grain boundaries. Let's go hyper-eutectic over here. Here we've got big bismuth crystals that's form first, and again these are big enough you can almost see them by eye if you polish the sample, and then there's eutectic solidification inside of that. If you go through this actually goes through this go back here under phase diagrams. This brings you through absolutely everything. If you would like to develop this, all the detail is there. So I'm just going to leave that there. If you find it useful, you have the tools to dig in. If not, no worries. And what I'd like to do is maybe go a little further and then say, the other thing that I would like to develop here at OSU, if there's interest for it, and please let me know if there would be interest for it. If there is, I'd be happy to see us do this, is as I said, some of these phases get pretty large. We get some blocks that can be almost micron or almost a millimeter across, or several hundred microns. That's something you can easily see at, say, 100x, and that's what you can get out of a laboratory microscope. So I think we could develop some processes where we could find ways you could polish these in a high school environment, look at them under a 100x microscope. This is something from Kenavision, and this is on the order of about $250. And I think with the next year of this MSP program, we could probably buy these for your classrooms if you would like to use it. And what's special about this microscope is there's actually an illumination stage above. You need lighting from above in order to do this. Most microscopes they use for biology and so forth just illuminate from below. To do metallurgical structures, you always have to light them from above, and this Kenavision microscope does that nicely. So the question I pose to you is really one, but if we could develop it so you could solidify and look at things that have been solidified under a microscope and see that they are a mixture of these solid solutions, and we can prove that, is that something that you would like to do in your classroom? The other thing that's in the other thing that the Cambridge site brings up nicely also is you go through these phase diagrams. Let me go back and do this. As you go through these phase diagrams, as you cool down, you fix the composition, and as you go cool with temperature, the other thing, if you plot temperature versus time, you actually see inflections here and here, and you see cooling rate, and then as you start to form solid, you see an inflection. When you hit the eutectic temperature, you see an arrest where the temperature doesn't change with time at all, and then it continues about with this initial slope again. So you can pick off these temperatures, and these temperatures this temperature A corresponds to that temperature, this temperature B will be fixed across here, that corresponds to that eutectic temperature. And again, this would make a nice graphing exercise if you've got and it's cheap to put a thermocouple into liquid metal and actually measure this, and this makes a nice lab that might be too advanced, but if you want to get into this, I could help support that. So that's my question. Would you if you're interested, I would be happy to help develop this, where we could do polishing procedures and everything, so we could examine this with the Kenavision. Tried and true example that is out there is this hot plate experiment. And this is one that's in the ASM camp, and Debbie Goodwin, Andy Neidham do this all the time. This is also up on Todd Bolenbaugh's Met Sci Teacher site. It's a nice example. It's basically what you end up doing is solidifying various compositions, including the eutectic here, put them all on a hot plate, and what you see is you can get these things near the eutectic composition melt at a much lower temperature than these guys here, and then you'll also see that when you're at some intermediate temperature, you get very mushy zones within that, and it's a little bit qualitative, but it's a nice demo, and that can all be done on a hot plate with the bismuth tin system. And I refer you both to what you've seen in the ASM course, and that website has that. You can do that. Other things you can do with this, as I mentioned, you can do sand casting, where you make basic impression in sand. You can pour this bismuth tin eutectic in there. The nice thing about this bismuth tin eutectic is this is about 150 degrees C is all you need to make that eutectic. So it works very nicely. You can also make investment casting, which is what you would do if you had just made plaster. And then these are silicone molds that also work very, very nicely. So, and this is one that I did. And again, the nice thing about these silicone molds is at 150 degrees C they hold up. So this is my eutectic automaton made out of bismuth tin. They don't scorch the molds. And again, you can go back and, you know, if you go for about $10 each, there's all kinds of molds that you can make, and you could have some fun with that. So two more examples. I'll show you how these phase diagrams can be important. What this means is if you can mix two metals, you can actually get a liquid phase at very low temperature. So this is temperature Kelvin. So room temperature is up here at about 300 degrees Kelvin. So aluminum gallium, if you can get gallium into aluminum, you'll get a liquid phase at room temperature. And you can do some insidious things with this. And this is what the microstructure looks like. What happens is the gallium diffuses along these intercrystalline boundaries and actually melts the material there if you can get the gallium in there. And there's a nice example on YouTube of what happens. This is an example from the Nerd Rage site that I'll show you in a second here. Let's see here. gallium. And I think if I just redo this, it should work. So here's a gallium-induced failure of a Coke can. And
Warning. Do not drink out of a can that has previously been treated with gallium.
And I know this doesn't
Sticks of gallium
work
and aluminum
really
alloys
great
may
after
accidentally be swallowed. Greetings, fellow nerds. In this quick video, we're going to weaken the structural integrity of a Coke can with gallium metal. Here I have an empty Coke can on which I'm placing a small dab of gallium that I previously melted in hot water. Now I'm using a glass pipette and scratching the aluminum underneath the gallium to break up the oxide layer and make the gallium diffuse faster. This is optional though. Now for the interesting part. As we time-lapse over half an hour, the gallium diffuses into the aluminum and alloys with it. You can see the aluminum start to contort as its internal structure is compromised by the gallium atoms. Now a lot of you might be asking where you can get gallium metal yourself. I got mine from a company called GalliumSource.com, which I've linked in the video description. They will also sell to individuals. If you use the coupon code NERDRAGE, then they'll also give you a 5% discount on everything they sell, so be sure to use that. Anyway, here is the Coke can. The structure is now incredibly weak. I can push through it with very little resistance. I'm not trying very hard at all. It feels like wet tissue rather than hard aluminum.
So that's a fairly nice demonstration. These phase diagrams matter. Again, to me, the incredible thing about all of this in the science is if you understand what's going on, you can be very predictive about that. And I'll show you that mercury has a very similar phase diagram. Therefore, you expect it'll do something very, very similar. And here's mercury on an aluminum beam. And this is linked to the next slide. There's mercury put on the beam, and you can see that it's diffusing in and causing havoc to the internal structure. There's I think, a poor explanation of this from Popular Science on. Actually, maybe the poor description is down here about it. It's the oxide layer. It's actually the mercury is going in and forming a liquid at the grain boundaries, and this can destroy that structure. This is a liquid metal embrittlement problem, and again, that can be explained all based on the phase diagram. So this is what aluminum gallium does, and what it does is it shows the three-dimensional structure also after the gallium goes in. It's a very thin layer that presents itself at the grain boundaries, and so this is what you're seeing are the intercrystalline boundaries. Now the crystals fit together, and it turns it liquid, or makes it a liquid solid mixture at room temperature, which is bad. And we can do a similar thing with mercury. And this is the site I just told you. Popular Science goes through this as well in this link. And they make 2 points there. Number one, TSA won't let you bring these liquid metals onto airplanes because you can wreak havoc with them. And it also makes the point that there are rumors that we did this to the Germans back in World War II, where we embrittled their aluminum planes using this bit of science. So again, science can solve problems or cause them if you don't use it right. So here's the summary of what we did today. Phase diagrams are a fundamental tool. We use them all the time in material science. Hopefully you see we get the number and type of each phase, the weight fraction of each phase, and the composition of each phase. That's provided we know the overall temperature and overall composition. We use this as a tool going forward to increase the tensile strength of materials, and solid solutions usually have increased tensile strength, but sometimes a decreased ductility. And then we can get these eutectics and eutectoids, and these really give you mixtures of solid solutions. And we can actually see those with microscopes. So that completes the lecture. Look forward to seeing you on the web, and we will have a somewhat familiar discussion and so forth about this soon. We'll hope to see you all on the internet soon. Thanks, and bye.